Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Models Part 5 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand number 1, the basics of shell model. Number 2, knowledge of magic numbers in nuclei. And number 3, the finer details of the shell structure in nuclei. Nuclear shell model. So, we continue our discussion about the nuclear shell model. Now, in the nuclear shell model, basically 3 nuclear potentials have been assumed. The harmonic oscillator potential, a square well potential and wood section potential. Now, first of all, the people tried the square well potential. Why people have considered a square well potential? Because people thought, or from the experimental observations, from the first experimental observations, it turned out, especially the experimental evidences which came from the Rutherford scattering experiment, that nucleus is spherical in nature. It means the nuclear potential is same everywhere within the nucleus, and outside the nucleus the nuclear potential is 0. So, people thought that the nucleus can be well described by a square well potential with Vr is equal to minus V0 for r less than equal to r and Vr is equal to infinite for r greater than r. So, to develop the nuclear shell model, people use the square well potential. But then further experimental evidences showed that nuclear potential is not uniform within the nuclear domain, but it falls off. It is basically have some value at the center, but away from the center towards the edges, it falls off gradually to become 0. Then the next generation physicists considered harmonic oscillator potential, but later on the further experimental evidences suggest that neither the square well potential nor the harmonic oscillator potential shows the correct behavior of nuclear potential, actual nuclear potential within the nucleus. So, they basically got some different kind of potential by fitting the nuclear density, observed nuclear densities for various nuclei, and then they fitted those at the nuclear densities with a function which is better called the wood section potential. So, according to them, then actual nuclear potential is neither harmonic oscillator type nor a square well type, but it is of wood section type. Now, the 3 potentials have been shown in the picture on the right hand side. You can see that the behavior of harmonic behavior of wood section potential is different than what the people have taken as harmonic oscillator potential or square well potential. Nuclear shell model, square well potential. So, the first generation of people who use the nuclear shell model, who developed the nuclear shell model, they considered the square well potential. So, we are going to discuss what comes out if we take the square well potential. So, square well potential is given by this, where k alpha square is equal to 2m u naught minus E alpha, where m is equal to 2m by h bar square. Now, since nucleus is a quantum mechanical system, so we have to apply quantum mechanics. In order to solve any quantum mechanical problem, we need to consider the Schrodinger wave equation and find out the Schrodinger wave equation, solution of the Schrodinger wave equation. So, in case of a square well potential, the Schrodinger wave equation is del square phi alpha plus 2m u naught minus E alpha phi alpha is equal to 0. The solution to this equation is psi r is equal to r n l r y l m omega. It means the solution, since the wave function phi alpha is a function of r theta and phi, the spherical polar coordinates r theta and phi. So, in order to solve this Schrodinger wave equation, we basically will use the concept of separation of variable. So, the solution to the equation is psi r is equal to r NL r y Lm omega. It means the total wave function is the product of radial wave function. Radial wave function depends upon the quantum number, the principal quantum number n and orbital quantum number L, and the azimuthal quantum number, that is YLM, where azimuthal quantum number depends on orbital quantum number. Azimuthal wave function depends upon the orbital quantum number and magnetic quantum number. Nuclear shell model, square well potential. So we continue our discussion about solving the Schrodinger wave equation for square well potential. So where the radial part of the equation is d square r NL over dr square plus 2r dr NL over dr plus k NL square minus L into L plus 1 over r square r NL is equal to 0. So according to separation of variable, we have separated out the variables. Now this equation is the Schrodinger wave equation in terms of radial wave function only. The solution on the radial part of the spherical Bessel function, so it means the solution of this radial part of the Schrodinger wave equation is given by r NL is equal to JL k NL r. For a deep well, we require JL k NL r is equal to 0. So this is the condition if we assume our nuclear potential to be deep enough. Nuclear shell model, square well potential. So here basically what we have shown is, we have shown the behavior of JL wave function, which is the function of k NL r, and 0 is its value is 0 where the wave function cuts the x-axis. So you can say that if we put J0x, if we plot J0x, J0x means k NL r is equal to 0. If we plot that Bessel's wave function, if we put that Bessel's wave function, we find that this wave function cuts the axis at different places. Similarly, we can have k NL r is equal to 1. So when we plot JL k J1 x is equal to J1x as a function of x value, so we find that this curve also cuts the x-axis at various places. In the similar way, we can assume different values of L like 0, 1, 2, etc., and then try to plot as a function of x. We find that these curves cut the x-axis at various places. The places where these wave function cut the axis will give you the numbers, that how many shells are there. For example, so here basically on the right hand side we have given the value of JLKR for different L value. For example, for L is equal to 0, JLKR is given by sin KR over KR. For 1, the value is sin KR minus KR cos KR over KR square. For L is equal to 2, the values are 3 sin KR minus 3 KR cos KR minus KR square sin KR over KR cube. So these are the values of JLKR for various values of L. Nuclear shell model, square well potential. So we still continue our discussion about the nuclear shell model when we consider the square well potential. So in the previous slide, we have seen that for various values of L, JLKR function cuts the x-axis at various places. So if we observe what are these places, what is the value of x, corresponding x where JL crosses the x-axis, we find that for L is equal to 0, JL crosses the x-axis at 3.1416, 6.2832, 9.4248, 12.5664 and so on, with decreasing amplitude. Similarly, for L is equal to 1, JLKR curve crosses the x-axis at 4.4934, 7.7253, 10.9041, 14.0662 and so on. So in the similar way, we can see that for various values of L, the JLK wave function cuts the axis at various places. Now, if we arrange, or before arranging these in terms of x value, now first of all we will define what is wave number k. Wave number k is k NLR is equal to xn, because we have seen that we are putting in the Bessel's wave function JLKR, we are putting kr is equal to x. So it means k NLR is equal to xnl, implies that k NL is equal to xnl over r, and the energy of state is given as ENL is equal to h bar c whole square over 2mc square into xnl square over r square, that is equal to E0 xnl square over pi square. Now, here in this slide, we are going to discuss the basic details of the basic things about the nuclear shell model. Now, first important thing in going or in applying the nuclear shell model is the concept of potential. First of all, we need to understand where does the potential come from. Interaction between nucleons in nuclei provides the necessary mean field or the potential, which depends upon the position but independent of time. It means that the interaction between nucleons in nuclei provide the necessary mean field or necessary mean potential. So, one of the basic assumptions of the nuclear shell model is that all the nucleons in the nuclear volume move in an average kind of nuclear potential, which is the result of the interaction between the nucleons within the nucleus. All nucleons move independent of each other in this mean field. Second assumption is, while the nucleons are moving in this mean field potential inside the nucleus, their motion is independent of the motion of other nucleons. Means every nucleon moves independent of other nucleons. Its motion is not affected by the presence of other nucleons. Third basic assumption is, the third important thing is that looking at the basic properties of nuclei, people have started thinking of what kind of potential can serve the purpose for solving the quantum mechanical problems for the nucleus. Since it was the beginning of the shell model, so people started working in the shell model, problem of shell model, by taking the simplest potentials. As from the experimental observations, it was clear that the nuclear potential was constant in the inner region. So it was thought that maybe the nuclear potential is of a square well type. But some experimental observations suggested that nuclear potential is constant in the interior region but falls off gradually towards the edges or towards the surface of the nucleus. So people thought that maybe the nuclear potential is of the harmonic oscillator kind of potential. But later on, the experimental observation suggested that the nuclear potential is neither of the square well type nor of the harmonic oscillator type, but is of intermediate kind of type, and Wood and Saxon basically plotted that density distribution, observed density distribution with the help of a function, and they could perfectly fit that density distribution within density distribution of nucleons in the nucleus with the help of that function. So they termed that function as the Wood-Saxon potential. So this was the third potential, or it is called more realistic potential as compared to the square well and the harmonic oscillator potential. So the people who were working to develop the nuclear shell model, they basically tried all three potentials. Now, nuclear shell model, square well potential. Now if we look at the solution in this slide, basically a table is given in which the solution of quantum mechanical problem assuming the square well potential is given. The sequence of solution is the first column K and L R values are given. The second column different orbitals, associated orbitals are given. Then the multiplicity factor is given, that is 2 into 2L plus 1, that how many number of nucleons in each orbital can have, in each orbital can occupy. And finally the sum of the number of nucleons up to the levels. So in the first column you can see that pi is the value where the first curve cuts the x-axis. It corresponds to L is equal to 0, that is 0s orbital. Number of nucleons is 2, sum is 2. The second cut is made by the same curve. Second time the same curve cuts the x-axis at value 4.49, K and L R value is equal to 4.49 for that, which corresponds to L is equal to 1, and L is equal to 1, since this is the first time that one value is coming, so it is 0p. So it's the p orbital. In the p orbital we can have 6 number of nucleons. So total sum up to that level is basically 8. Third time when the curve crosses is at 5.79, which is L is equal to 2, and it corresponds to 0d. Since it is a d orbital, so capacity of this d orbital is 10. So total number of nucleons up to that level is 18. In the same way, the different number of nucleons are basically shown at different number of orbitals. Nuclear shell model, harmonic oscillator potential. So now here in this slide we are going to discuss the development of nuclear shell model when harmonic oscillator potential is considered. Now Schrodinger wave equation is given by minus h bar square by 2m del square plus Vr psi r is equal to E psi r, and the energy eigenvalues are given by E is equal to h bar omega nx plus ny plus nz plus 3 by 2 is equal to h bar omega n plus 3 by 2, where n is the principal quantum number 0, 1, 2, 3, 4, etc. Now energy depends only upon n and not on nx, ny, nz. It means since the energy depends only on the capital N, which is the principal quantum number, and not on the projection of those quantum numbers on the 3 axis, so it means that corresponding to one value of capital N, there can be various combinations of nx, ny and nz, which implies that the energy levels are degenerate. In general, we have Nn is equal to n plus 1 into n plus 1. This is the, you can see it as a splitting, you can see it as the degeneracy associated with a level. Nuclear shell model, harmonic oscillator potential. So still we are continuing our discussion about the nuclear shell model when harmonic oscillator potential is assumed. Now in terms of polar coordinate system, so in the previous slide we considered the Cartesian system. Now we want to see the situation when we considered polar coordinate system. In the polar coordinate system, capital N is given by 2 nr plus 1 minus 2, that is, and nr is equal to n plus 1. En is equal to n plus 3 by 2 h bar omega is equal to 2n plus L plus 3 by 2 h bar omega. One can find capital N is equal to 2 into small n plus L, where n is equal to 0, 1, 2, etc. and nr is equal to 1, 2, 3, 4, etc. radial quantum number. So in case of oscillator, we have the combinations of nrl, which is equal to 1s, 1p, 1d, 2s, 1f, 2p, 1l, 2d, 3s, and energy levels are basically, these are the oscillator energy levels. Next one is 1h, 2f, 3p, 1i, 2g, 3d, 4s, etc. and so on. Nuclear shell model, harmonic oscillator potential. Now here we can see that on the left hand side a table is given in which various values are represented, like n value, corresponding energy value, orbitals, which orbitals are involved, then Nn is equal to n plus 1 into n plus 2. So, it means it is basically the degeneracy associated, and then sigma n Nn. So, for example, for n is equal to 0, there is only one level, and that is 1s, and the energy of this level is 3 by 2 h bar omega. If we want to find what is the value of Nn, so then Nn is equal to 2. Again, for n is equal to 1, E is equal to 5 by 2, that is 1p, orbital is involved, say 6 number of nucleons will be there. So, likewise, for different values of n, we have different energy of the orbitals and different number of orbitals involved. If we plot them as a function of excitation energy, we find that the plot looks like the one given on the right hand side of this slide. So, here first level, second level, third level, fourth level, fifth level, sixth level, 7, all these levels are given. So, if we start filling the nucleons with the maximum capacity of the orbitals involved, we find that from the bottom, if we go to the top, we find that various only few energy levels basically can give rise to magic number, like 2, 6, 10, 14, 18, 22, 26, etc. So, students, let us summarize what we have learned in this module. We have discussed number of concepts in this module, but what ultimately we have learned so far, we are going to discuss in this slide. The first thing we learned is that mean field is provided by the interaction among nucleons in nuclei. Second thing we learned is that to get nuclear magic numbers, 3 potentials were suggested. Third thing we learned is that a square well and harmonic oscillator potential could reproduce only first 2 magic numbers. The next thing we learned is that nuclear potential is neither perfect square well type nor harmonic oscillator type.